Okay, everybody, this lesson is on some of the special factoring patterns that we have. The first pattern that we'll talk about is called the difference of squares. Difference of squares. And it looks like this. If we have something like a squared minus b squared, that will factor to a plus b times a minus b. And you can easily verify this if you were to FOIL out the right side using the FOIL method. You would get a squared minus b squared. Some examples of using the difference of squares pattern. X squared minus 9. This is x squared minus 3 squared. And so it is going to factor to x plus 3, x minus 3. Here's another one. Y squared minus 49. That is y squared minus 7 squared. And so that's going to factor to y plus 7, y minus 7, according to the pattern. For x squared minus 25 is also a difference of squares pattern. It is 2x squared minus 5 squared. And so in this case, the 2x is like the a in the pattern and the 5 is like the b. So following the pattern, again, we will have 2x plus 5 and then 2x minus 5. Nine a squared minus 16b squared. Okay, this is also a difference of squares. It is 3a quantity squared minus 4b quantity squared. And so following the pattern, this is going to be 3a 3a plus 4b and then 3a minus 4b, just like that. Okay, now let's look at one that's a little bit different here. M plus 3 squared minus excuse me z squared. Okay, this is a difference of squares. You got this m plus 3, which is being squared, minus this z squared. And so I'm just going to follow the pattern just like I've been doing. It's going to be m plus 3 plus a z, and then m plus 3 minus a z, and we have it factored. Just a couple more of these difference of squares. Two x squared minus 72. Now, the way it is right now, it's not really a difference of squares, but you got to recall whenever you're factoring, you always want to check to see if there's a GCF, which will factor out first. And in this case, we do have a 2, which we can factor out first. So we've got 2 times x squared, and this will be minus 36. Now, what we have left in the parentheses is a difference of squares, so I'm going to factor that. It's going to be x plus 6 times x minus 6. And we have it completely factored. Y to the 4th minus 16. Now this can be thought of as y squared squared minus 4 squared. And so if I follow the pattern, this is y squared plus 4, y squared minus 4. However, on this one we are not done yet, because right here, y squared minus 4 is yet another difference of squares. And that factors to y plus 2 times y minus 2. This part right here goes there, like that. Now you might be asking about this. Y squared plus 4 is not a difference of squares, it's a sum of squares, and all sums of squares are prime. Sums of squares are all prime. You cannot factor them, so don't even have to bother trying. Okay, and so we have this completely factored right there. Okay, one more of these difference of squares here. one more. X squared y squared minus minus 4z squared. Okay, we're going to write this as xy quantity squared minus 2z quantity squared. So it is a difference of squares, this squared minus this squared. And so following the pattern, we should have xy plus 2z and then xy minus 2z. All right, and that is our difference of squares pattern. The next pattern that we're going to talk about is the sum of cubes pattern. Sum of cubes. And let me write it, I'm going to write it in reverse here for you. If I were to take x minus y, I'm sorry, x plus y that is, and multiply to x squared minus xy, come on, there we go, minus xy plus y squared, multiply all that together, a lot of terms would cancel and we would end up with just x cubed plus y cubed. And so if we think of that in reverse, that means that x cubed plus y cubed will factor to that. Here's an example of how we can use this pattern to factor a sum of cubes. Let's say, for instance, we have a cubed plus 27. Now I know that this is a sum of cubes because this is a cubed plus 3 cubed. And so I'm going to replace the a, or sorry, the x is up here in the pattern with the a, and the 3 is like our y in the pattern. And so this is going to be a plus 3. That's the same as my x plus y here. X squared is a squared. Minus xy for us here is going to be minus 3a. And then plus y squared is our 3 squared, which is going to be 9. And I have it factored right here. Okay, it's factored. This trinomial that you get from these cubes is always prime, so it will not factor further. You don't need to try. That's as far as this one would go. Here's another one. 8p cubed plus 125. All right, now this is a sum of cubes because I can write it as 2p quantity cubed plus 5 cubed. And so the 2p will replace the x in the pattern, and the 5 will replace the y in the pattern. Let me write the pattern out for you here. So this is my x here, and that's going to be my y right there. So x plus y here will be 2p plus 5. X squared is this 2p squared, which is going to give me 4p squared. Minus x times y is 2p times 5, which is 10p. And then finally y squared is our 5 squared, which is going to be 25. And I have it factored. Okay, that's our sum of cubes pattern. Let's do one more of those. Let's turn the page here. One more example of a sum of cubes pattern. 2x cubed plus 2,000. Now, as I mentioned earlier, you always look for a GCF that you can factor out first, and in this case it'd be a 2. 2 times the quantity x cubed plus 1,000. What I have in the parentheses here is a sum of cubes. It's x cubed plus 10 cubed. And so if I follow the pattern correctly, move that out of the way, 2 times, let's see, our x plus y will actually be x plus 10 here, and then our x squared minus 10 times x, and then 10 squared is 100. And I have it factored. Sum of cubes. All right. We also have what's called a difference of cubes pattern. Difference of cubes. And it looks very, very similar to the sum of cubes pattern, except there's a couple sign changes. X minus y times x squared plus xy plus y squared will multiply out to x squared minus y, x cubed minus y cubed. And so x cubed minus y cubed factors to this right here. Let's do an example of using this pattern. 27m cubed minus 64. This is 3m quantity cubed minus 4 cubed. So it fits the difference of cubes pattern. Here's the pattern. And so for us, we're going to fill in for x minus y, 3m minus 4. X squared here is 3m squared. You got to square the 3 and the m, so that's going to be 9m squared. Plus x times y for us will be 3m times 4, which is 12m. And then we have y squared, which in our case will be 4 squared, which is a 16. And I have it factored. And here's another example of the difference of cubes pattern. 27 a cubed minus 8b cubed. This is 3a to the third power, and this is 2b to the third power. And so following my pattern, I'm going to have 3a minus 2b times 3a squared, so that's 9a squared, plus x times y, that's going to be 3a times 2b, which is going to be a 6ab. And then finally 2b squared, so that'll be a 4b squared. And I have it factored yet again. So those are our difference of cubes patterns that we have. The other type of pattern that I'm going to mention is the what's called the perfect square trinomial patterns. And they look like this. If I had x squared plus 2xy plus y squared, that's going to factor to x plus y quantity squared, to what we call a perfect square. You could easily check that this is true if you were to take this left side here and FOIL it out correctly, and you would get this. If there is a minus sign instead, minus 2xy, then we have an x minus y quantity squared for our pattern. Now, you don't really need to have these patterns memorized for factoring, because you could just use the regular method we have for factoring trinomials. Here's an example of what I mean. Let's say we have z squared plus 12z plus 36. Now, if I factor that, like we've done in a previous section, that's z times z, and then 36 and 12, the two numbers are 6 and 6 that we need. So it's plus 6 and plus 6. Now, I did not need really these patterns at all to do this. This is z plus 6 to the second power. And what that tells me is that what we had here was a perfect square, because a perfect square trinomial, that is. And that is because it factored to a quantity squared. Here's another example of a perfect square trinomial. 144p squared minus 120p plus 25. Okay, so we attempt to factor it here. We'll just use our trial and error method. 144p squared, why don't we try 12p and 12p? After all, you multiply those and you will get 144p squared. Factors, or actually negative factors of 25. 25 is negative 5 times negative 5. Let's put that in. Let's just check and make sure we have this right. Checking my middle term. That's negative 60p. That's negative 60p. And that adds up to negative 120p, so it is correctly factored. And so I wouldn't leave it like that since they're identical. This is 12p minus 5 quantity squared. And I factored it. Here's a couple more. (49z squared minus 14z times k plus k squared). Okay, so we're going to attempt to factor it here. Let's take a good guess here. 49z squared looks like it's going to be 7z times 7z. Let's try it. 7z times 7z. K squared, now since there's a negative sign there, why don't we try negative k times negative k. Plug it in. And we do have it correctly factored if we check the middle term. That's 7zk and 7zk, which adds up to negative 14zk. So we do have it correctly factored. Of course, we write that as 7z minus k quantity squared. Here's one more example of a perfect square trinomial. And that would be 9a squared plus 48ab plus 64b squared. So let's try for 9a squared, let's try 3a times 3a. And for 64b squared, we're going to try 8b times 8b. So I'll plug those in. Let's check the middle term just to make sure. That times that is 24ab. This is a 24ab, and that does add up to 48ab, correct middle term. And so this is a perfect square trinomial. It factors to 3a plus 8b quantity squared. And that is our perfect square trinomials, and the end of this section.